Welcome back, everyone, to the Deep Dive, where we like to get our hands dirty with some of the latest and greatest research papers in AI and ML.
Yeah.
And today's paper is, it's a really interesting one. It's about how to make large language models better at reasoning, LLMs, everybody's talking about them.
Yeah.
And these researchers have come up with this really cool idea about getting them to actually collaborate with each other and use a shared memory. Like imagine, it's almost like building a team of AI experts, right? Each of them with their own little specialty or way of looking at a problem.
Right.
And they can all share what they know and learn from each other.
Yeah, and build on each other's knowledge.
Exactly. And this is getting super important, making LLMs better at reasoning. I mean, we're using them for more and more things all the time.
Absolutely.
So, we really need them to be reliable and accurate, right?
Yeah, especially as we're entrusting them with more and more complex tasks. It's not just about generating creative text anymore. It's about, actual problem-solving, decision-making.
Right.
And for that, you need robust reasoning.
Okay, so the big question this paper is trying to answer is, how do we get these LLMs to reason better, to go beyond what a single LLM can do on its own?
Yeah, how do we break through those limitations? Because we know individual LLMs, while impressive, they can still make mistakes, they can be inconsistent.
Right.
So this research is exploring whether having multiple LLM agents working together and drawing on this shared memory, can we get to a point where they reason more reliably and more accurately than any single LLM could?
Like a true team effort.
Exactly.
All right, so let's dive into the specifics here. They call this a continuous collaborative learning system for LLM agents.
Right.
So what that means is basically you have these multiple LLM agents, right? And they're all working together on these reasoning tasks. They might be using different approaches, different ways of thinking about the problem.
Yeah, different strengths.
And they're all contributing to this shared pool of knowledge, this memory bank that they can all tap into.
It's a really elegant idea because it mirrors how, in a lot of ways, humans solve problems.
Yeah.
We rarely do it in isolation. We rely on our past experiences, on the knowledge of others.
Right.
And this system is kind of trying to replicate that in the world of LLMs.
So to break this down a bit further, the paper looks at three key areas. One is the different styles of reasoning that these agents can use. Then how they can best collaborate with each other. And finally, how this shared memory bank is actually created and used.
It's the nuts and bolts of the whole system.
And our mission today is to really get a grasp on these innovative approaches and try to understand, what this paper reveals about how to make LLMs reason better.
It's all about pushing the boundaries of what's possible with these models.
So to start off, let's talk about these reasoning styles, the different ways these agents can approach problem.
The tools in their reasoning toolbox, so to speak.
Okay, so first up, we have direct prompting. That's the most straightforward, right?
Yeah, the simplest one.
You just give the model the question and say, hey, figure this out.
See what you can do.
And sometimes that works, but for more complex tasks, you need something a little more sophisticated.
Exactly.
So then we have chain of thought prompting, which is, they call it ZCOT for zero-shot chain of thought, and NCT for few-shot chain of thought. And the idea here is you're basically prompting the model to think step by step.
Right. You're encouraging it to break down the problem into smaller, more manageable chunks.
Like you're saying, okay, don't just jump to the answer. Show me how you got there.
Yeah, show your work.
And with few-shot chain of thought, you're actually giving the model some examples of this step-by-step reasoning in the prompt.
So it's like you're providing a template for how to think through the problem.
Right, like a little bit of guidance.
Yeah.
And finally, there's analogical prompting, or AP. This one is interesting because you're essentially asking the model to come up with its own relevant examples.
Ooh, that's cool.
Yeah.
So it's not just relying on examples you give it. It has to find its own connections and analogies.
Yeah, like you're saying, okay, you've seen similar problems before. How did you solve those?
Right. Use your past knowledge to figure this out.
And this can be really powerful for tackling new and unfamiliar problems.
It's almost like encouraging a more creative problem-solving approach.
So each of these reasoning styles has its own strengths and weaknesses, right?
Yeah, there's no one-size-fits-all solution here. Direct prompting is quick and simple, but it might not cut it for complex tasks.
Right.
Chain of thought is great for breaking down problems, but it depends on how well you craft those prompts. And analogical prompting is all about tapping into the model's ability to make connections, but that can be tricky too.
So the choice of reasoning style really depends on the specific problem and the capabilities of the LLM.
It's about understanding the tools and using the right one for the job.
Okay, so we've got our different reasoning agents. Now, how do we get them to work together effectively?
Right, the collaboration is key here.
So they tested a bunch of different collaboration methods, starting with a baseline, which is just a single greedy agent.
Yeah, so that's like the control group, just one LLM trying to solve the problem on its own.
No help from its friends. Then they looked at self-consistency, or SC. This is where you basically get the model to generate multiple responses.
And then you vote on the most common answer.
You introduce a little bit of randomness through something called temperature sampling.
Right, so it's not always giving the exact same answer. It's exploring different possibilities.
And then, by taking the most frequent answer, you're hoping to get a more reliable result.
It's like getting a second opinion, or a third, or a fourth.
Right, and the thinking is that if the model keeps coming up with the same answer, even with a bit of randomness, it's probably onto something.
Yeah, it increases your confidence in the solution.
Now, they also introduced this idea of varied context agents. This is where things start to get really interesting.
Yeah, this is where the collaboration really starts to shine.
So when you're using few-shot prompting, right, you're giving the model some example reasoning stats.
Right, those exemplars we talked about.
With varied context agents, each agent gets a different set of exemplars.
Ooh, I see.
So they're all seeing the problem through slightly different lenses, right, based on the examples they've been exposed to.
It's like having a team of specialists, each with their own area of expertise.
Yeah, and then they all get to vote on the final answer.
So you're leveraging the diversity of perspectives to hopefully arrive at a more robust solution.
It's almost like crowdsourcing the reasoning process.
Exactly.
And they also explored using a summarizer agent instead of just voting.
So instead of a simple majority rule,
Yeah.
you have this higher level agent that weighs the evidence.
Right. So the summarizer agent takes all the outputs from the other agents, their final conclusions, or even their step-by-step thought processes, and it tries to synthesize a final answer.
It's like having a judge or a panel of experts reviewing the argument.
Yeah, like a final check to make sure everything makes sense. Okay, let's talk about memory, because this whole system relies on the idea of these agents having a shared repository of knowledge, right?
Right, a place to store their experiences and insights.
So the paper investigates two main types of memory banks: frozen memory and learned memory.
Okay, so what's the difference?
Well, frozen memory is created once at the beginning. They did this by having a single strong LLM use zero-shot chain of thought on the training data, and then they store all the questions it answered correctly along with its reasoning.
So it's like a precompiled library of solved problems and their solutions.
Exactly. It's fixed, it doesn't change. Learned memory, on the other hand, is built up gradually. As the multi-agent system is training, if an agent solves a problem correctly by using the existing memory, that problem and its solution get added to the bank.
So it's constantly evolving, growing with the system's experience.
Yeah, it's like a dynamic knowledge base that gets richer over time.
A living document of the system's learning journey.
Now, how do these agents actually access the memory? How do they find the information they need?
Right, because having a memory is one thing, but knowing how to use it effectively is crucial.
So they tested a few different retrieval methods. One was using a small, fixed set of exemplars that are just used for every problem.
Okay, so that's like having a go-to set of examples that you always consult.
Right, a basic toolkit. Then there's random sampling, where you just pick a few examples at random from the memory bank for each new problem.
Interesting. So it's not about finding the most relevant examples. It's about introducing some variety, some randomness into the mix.
Yeah, and the thinking there is that it might help the agents avoid getting stuck in a rut, always looking at the same kinds of examples.
Right, because sometimes a fresh perspective, even if it's not directly related, can spark a new line of thinking.
And finally, they tested similarity-based retrieval. This is where they use something called embeddings. Think of these as like numerical fingerprints that capture the meaning of the questions.
Okay, so it's a way to represent the semantic content of the question in a way that the computer can understand.
Right, and they use something called gecko embeddings for this. So the idea is to find the examples in the memory bank that are most similar to the current problem.
So you're trying to retrieve the most relevant past experiences.
Exactly.
To help the agents solve the problem at hand.
Okay, so to put all these pieces together, they designed a series of experiments.
Right. Time to put these ideas to the test.
What models did they use and what kind of tasks were they tackling?
So they primarily used the Gemini 1.0 Pro and Gemini 1.0 Ultra models. These are known for their strong reasoning capabilities. So they're a good choice for this kind of research.
Right. You want to make sure you're starting with a solid foundation. And for tasks, they chose 3 from the big benchmark: Folio, which tests first-order logic; RACO, which involves reasoning about colored objects; and TSO, which is about tracking shuffled objects.
So a good mix of logical and spatial reasoning challenges.
Yeah, they wanted to cover a range of different reading skills. And the key here is that they systematically tested all these different combinations of reasoning styles, collaboration methods, and memory configurations.
Right. It's about seeing how all these pieces fit together
Hmm.
and what leads to the best performance.
And I'm sure you're dying to know what they found.
Oh, absolutely. Spill the tea.
Well, there were some pretty surprising results. One of the big ones was that the varied context agents, the ones with the different sets of examples, actually performed really well.
Interesting. So having that diversity of perspectives really paid off.
Yeah, they often did just as well as the simpler self-consistency method, which was kind of unexpected, because you'd think that having more consistent responses would be better, right?
Yeah, you'd assume consistency is key for reliability.
But it turns out that sometimes having those different viewpoints can lead to a more robust solution.
It's like in a brainstorming session. Sometimes the most unexpected idea can lead to the best outcome.
Another really interesting finding was that random sampling from the memory often outperformed the similarity-based retrieval.
Wait, what? That's counterintuitive. You'd think that finding the most similar examples would be the most helpful.
I know, right? But the author suggests that maybe this is because random sampling exposes the agents to a wider variety of information.
Oh, that makes sense. It's preventing them from getting stuck in a narrow line of reasoning.
Right. They're not just looking at the same kinds of examples over and over again. They're getting a broader perspective.
It's like the difference between only reading books in your favorite genre versus branching out and exploring different topics.
Exactly. You might discover something new and unexpected that actually helps you solve the problem. And it also suggests that maybe over-indexing on similarity could create a kind of confirmation bias in the model.
Interesting thought. Like it's only looking for evidence that supports its existing beliefs.
They also found that the frozen memory, the one that's created once at the beginning, actually performed just as well as the learned memory. And it was much more efficient to create.
So that's a big win for practicality. Because building and updating a large memory bank can be computationally expensive.
Right. So if you can get the same performance with a simpler, more efficient approach, that's a huge advantage. And analogical prompting, remember that one, where the model comes up with its own example.
Yeah, the one that taps into the model's creativity.
Well, that turned out to be more robust to changes in the memory and the choice of few-shot examples.
So it's more adaptable, less sensitive to those design choices.
Yeah, it seems like when the model generates its own analogies, those examples are inherently more flexible.
They're tailored to the specific problem at hand.
How about the collaboration aspect? Did they find any particular way of distributing the workload or information was more effective?
So they found that giving different sets of examples to different agents, like spreading those exemplars among the varied context agents, generally led to better performance.
So again, diversity wins the day.
It's like the old saying, 2 heads are better than 1. But in this case, it's more like several heads, each with different experiences, are better than 1.
And the summarizer agent, remember that guy? The one who tries to synthesize all the information? Well, he seemed to be most useful when the individual reasoning agents weren't that strong.
So it's like a good leader can really elevate a team, especially when the individual members might be struggling.
Right. If the underlying reasoning is already high quality, the summarizer doesn't add much. They also did some head-to-head comparisons between different techniques, like analogical prompting versus chain of thought.
Yeah, always good to see how different approaches stack up.
And they found that analogical prompting tended to do better on the folio logic tasks and the RCO colored objects task, whereas chain of thought was stronger on the TSO shuffled objects task.
Interesting. So the best approach really depends on the nature of the problem.
Yeah, there's no one-size-fits-all solution. And those model-generated examples in analogical prompting can be really effective for certain types of reasoning. And when they compared giving more examples to a single agent versus using varied context agents with fewer examples each, but with the same total number of examples, often the varied context approach came out on top.
So again, diversity is key, even when you're working with the same amount of information.
Now, it's important to note that they did see some cases where accuracy actually dropped.
So it wasn't all sunshine and roses. There's some stumbling blocks along the way.
Yeah, sometimes things didn't go as planned. And they suggested a few possible reasons for that. Sometimes the random examples from memory might have been just bad luck. They just happen to be irrelevant or misleading. And in other cases, especially with the learned memory, they suspected that the system might have struggled to learn and retain truly helpful examples.
So there's still work to be done in terms of ensuring the quality of the data that these models are learning from.
Right, garbage in, garbage out, as they say. Okay, so let's take a step back for a second and think about the bigger picture. Where does this research fit into the broader field of machine learning?
Right. How does this connect to what's come before?
Well, this work really builds on the foundations of in-context learning, where models learn from examples provided in the prompt, and the chain of thought prompting technique, which encourages more detailed step-by-step reasoning.
So it's taking those existing ideas and pushing them further.
Yeah, and the move towards multi-agent systems is a natural progression in trying to achieve more robust and generalizable AI. We've seen similar trends in other areas of machine learning, like with ensemble methods, where combining the predictions of multiple models often leads to better performance, right? It's the wisdom of the crowd applied to AI. And giving LLMs a memory is clearly inspired by how humans learn. We're constantly building on our past experiences, right, referencing and updating our knowledge. It's not like we start from scratch every time we face a new problem.
Exactly. We have this vast reservoir of knowledge and experiences to draw from. And this paper is exploring how to give LLMs that same capability.
So this paper connects to a lot of existing research on multi-agent systems, like self-consistency, debate-based approaches, and meta-prompting. And there's also been a lot of work on memory augmentation for LLMs, creating task-specific knowledge bases and using episodic memory. So this paper brings together and expands on these different threads in a really novel and compelling way.
It's a synthesis of ideas that pushes the field forward.
All right, let's try to distill some key takeaways for our listeners. The big, non-repetitive points that really stood out from this research.
The nuggets of wisdom.
Firstly, that random memory retrieval can actually be super effective, sometimes even better than similarity-based retrieval. That was a big surprise. It challenges our intuitions about how LLMs learn and suggests that diversity of information is really important. Secondly, using a static pre-built memory bank like frozen memory can be just as good as a constantly updated one, and much more efficient.
So that's a big win for practicality.
Thirdly, distributing different examples among collaborating agents is better than concentrating them.
Again, diversity wins the day.
And finally, the best approach really depends on the task and the model. There's no one-size-fits-all solution. So what are the real-world implications of all this? Where could this research lead us?
Well, I think this could really change how we design AI systems for complex problem solving. Imagine teams of AI agents collaborating on scientific discoveries, analyzing huge data sets, and building on a shared memory of research findings.
That's a pretty exciting vision. Or in finance, AI agents with different analytical approaches, working together to identify market trends and assess risks.
It could revolutionize how we make decisions.
And even in fields like law or engineering, collaborative, memory-augmented LLMs could tackle really intricate problems.
More effectively than individual systems ever could.
The possibilities are pretty mind-boggling. And the efficiency of frozen memory makes it more feasible to deploy these advanced AI systems, even in environments with limited resources. Okay, so now for our favorite segment, novel notions, where we like to brainstorm some potential future research directions inspired by the paper. What ideas has this sparked for you?
Well, one thought I had builds on this whole memory aspect and the fact that sometimes including examples can be distracting. What if we created something called adversarial memory banks?
Adversarial memory banks. That's interesting. Tell me more.
So the idea is to have some agents that are specifically tasked with contributing misleading or edge case examples to the memory.
Whoa, so you're intentionally trying to trip up the system.
Not to break it, but to make it stronger. The goal is to force the other reasoning agents to become more discerning, to really think critically about the information they're retrieving.
So it's like a built-in stress test.
Exactly. You're constantly challenging the system to improve its reasoning.
I like it. Can you give me an example?
Sure. Imagine you're using this system for financial analysis. You could have these adversarial agents introduce scenarios with deliberately misleading data points, and then you see if the other agents can identify and disregard that bad data.
So it's like training the AI to be more skeptical.
Exactly, to double check its sources.
That's pretty clever. What's your second novel notion?
Well, the paper used a fixed setup of agents. But what if we had a system that could dynamically adjust the number and types of reasoning agents it uses, based on the specific problem and the current state of the memory.
So it's like a self-adapting team of AI experts.
Exactly. It could learn over time which agent configurations work best for different situations.
Give me an example.
Sure. If it encounters a really complex logical puzzle where different analogies might be helpful, it could dynamically allocate more varied context agents. Or if the agents are kind of stuck, unsure of the answer, it could bring in a stronger summarizer agent to help make a decision.
That's fascinating. It's like the AI is learning how to manage its own team.
And this could all be driven by reinforcement learning, where the system learns over time which agent combinations are most effective, leading to more efficient and targeted reasoning.
Both of those are really thought-provoking ideas. They highlight just how much potential there is in this area of research.
Yeah, it's an exciting time to be working on AI.
Well, this has been an incredibly insightful deep dive. This paper really offers a compelling vision for building more intelligent and collaborative AI systems. And the surprising results about random memory retrieval are definitely something to think about. We highly encourage everyone to check out the paper itself. The link is in the show notes. It's packed with even more details and insights. And as we continue to develop more and more complex AI, this research raises a crucial question. How do we balance the power of collaboration with the need for individual reasoning and critical evaluation?
Right. We don't want to create a system that just blindly follows the crowd.
Yeah.
We need to make sure these AI systems can think for themselves and challenge assumptions.
It's a delicate balance, but it's one that's going to be essential to get right. Thanks for joining us for this deep dive. We'll be back next time with another look at cutting-edge research.
See you then.